excellently and speaks excellent as well. I enjoy reading his blog, and please go ahead with your.
Thank you. It's a great honor to speak at Erdős's Centennial Conference. As Imre said, I did meet Erdős once when I was 10. I guess that makes me an epsilon, maybe a delta, I'm not sure. Yeah, so he was visiting Australia. I think he was visiting George Zekeres, I think, a good friend of his. He stopped by Adelaide, my hometown, and I think I was at a prize ceremony for a high school math competition or something. And he met with me, and he discussed with me a math problem, which unfortunately I don't remember. I really wish I had retained those notes. I was 10, I didn't quite realize how precious these things were. But I do remember talking with him, and I think the one thing that struck me was just how much he sort of treated people like me as an equal. You know, I would ask questions, which, you know, a 10-year-old asking questions is very naive, and, you know, he would just nod and answer them very respectfully. And I really, I don't know, I was really impressed by Paul. And later on, actually 6 years later, he wrote me a letter to get into graduate school in Princeton. So I'm very grateful for him for helping me start my own career. Okay, so I'm going to talk about the joint work of Ben Green, who, by the way, is not at UCLA, is at Oxford right now, on some classical problems in incidence geometry, combinatorial incidence geometry, in particular about points and lines. The setup, the setup is that we have n points in the plane, so let P be a set of n points in the plane. Initially, this will be the affine plane, R2, but actually we'll soon move to the projective plane. So given n points, you define a k-rich line to be a line that contains k of the points, exactly k points of your set. If a line contains exactly 2 points, that's called an ordinary line. So you have n points sort of in generic position, then you n choose 2 ordinary lines, but if they're not in general position, you can have fewer ordinary lines. We let n sub k be the number of k-rich lines. So you have n2, n3, n4. We don't discuss n1 because that's infinite. And the general question, sort of vague, is if you fix the number of points n, what can you say about nk for various k? What are the various possible values of nk? Now, that's quite a vague question. There are many sub-questions which are interesting. I should, of course, mention a reasonably famous, not so famous, but reasonably famous question of Erdős on this topic, which is that if you have a configuration for which no 5 points lie in a line, so n5, n6, n8, and so forth, or 0, does that also mean that n4 is small, that there can't be too many 4 tuples that are concurrent if there are no 5 tuples that are concurrent? There's a reason why this starts at 4. This is not true at 3. But, so that's a nice question. He offered $100. I don't know if he can still collect it, but okay. Unfortunately, we won't touch that question. Actually, I've still yet to answer the Erdős question. I still have as one of my life ambitions. But anyway, so we're going to focus just on the smallest ends, the n2 and n3, number of ordinary lines and 3-rich lines. Okay. So here, of course, is just a simple example. Here's a configuration of 7 points, a triangle, and the midpoints and the median, and the centroid. And you have 3 ordinary lines. The ones in red go through 2 points, and then 6 other lines that are 3-rich. That's a typical configuration. Okay, so classically we face this problem in the plane, the affine plane R2, but actually it's more natural to phrase things in the projective plane because the problem is invariant under projective transformations. You take any projective transformation of R2, or the projective plane, that maps n points to n other points, and lines map to lines, and incidences map to incidences, and so the number of ordinary lines don't change. The number of k-rich lines don't change. So it doesn't make any difference if you work in the projective plane or Euclidean plane. if you have k points in the projective plane, you can apply the probabilistic method. So you apply random transformation mapped into the affine plane. And so it's an equivalent question. But it's more convenient mathematically to work in the projective plane. One of the reasons is that in the projective plane, we have projective duality. Every point in the projective plane is dual to a line. Every line is dual to a point. So instead of talking about n points and asking about k-rich lines, you can talk about n lines and talk about k-rich points, and it's an equivalent question. And we'll see that we will need duality later on. Okay, so we will actually be working in the projective plane. Okay, so there are many theorems about k-rich lines. Perhaps the most famous one, rather appropriate for this conference actually, is the Sylvester-Gallai theorem, which was first posed as a question by Sylvester in 1893. And this is actually the way that he posed the question. So in the notation that we just set out, the statement is that if you have n points in the projective plane, and they're not all collinear, so they don't all lie in one line, then you can find at least one ordinary line that at n2 is at least 1. Okay, of course, if they're all collinear and there's 3 points or more, then there aren't any ordinary lines, but that's the only way you can get rid of ordinary lines, to make them all collinear. So that's a great theorem. So it was posed by Sylvester in 1893. It was posed again by Erdős like 50 years later, I think independently of Sylvester. And it was actually, but it has many, many proofs. So Melchior, I think, had the first proof in the literature, even predating Erdős. Then I think Gallai answered Erdős's question shortly afterwards, and then there are several other proofs. The most famous one is Cayley's proof, which I will review very shortly. But that's actually not the one that we use in our argument, but I'll review it anyway because it's so pretty. I'll say one thing about Sylvester-Gallai theorem is that it's very important that we work over the real line. So just the Sylvester-Gallai theorem says that if you're in the real projective plane and you're not collinear, then you have an ordinary line. So this theorem is non-trivial. Well, one way to see that is non-trivial is that if you replace the real line by other fields, the statement is false. So, for example, if you work over finite fields, you can just take the entire finite field plane, f squared, and that's a set with no ordinary lines as long as the finite field has more than 2 elements. And then a little bit less obviously over the complex plane, well, complex line, so C2, the complex plane, 4-dimensional. The Sylvester-Gallai theorem is also false. There's a special configuration called the Hess configuration, which I'll review in a little bit, of 9 points in the complex plane with no ordinary lines and not concurrent. So what this tells you is that if you want to prove the Sylvester-Gallai theorem, at some point you must use a special property of the real line. Okay, you can't just use the fact that it's a field. You must use something else. Okay, so the standard proof is Cayley's proof. Very, very pretty. Erdős would call it a proof from the book. You probably even, in Hungary, I wouldn't be surprised if you teach in primary school this particular proof. I mean, you can teach it in primary school to a bright student. Probably most of you already know it, but I just review it because it's so pretty. So here is Cayley's proof of the Sylvester-Gallai theorem. Suppose that you prove by contradiction. Suppose that the Sylvester-Gallai is false. So you have n points, not all collinear, but no ordinary lines. So every line that passes through 2 points also passes through a third. Okay? So there's no ordinary lines. Sorry, they're not all concurrent. So you can find a point P. This doesn't work. You can find a point P and a line L which doesn't lie on P, not incident to P. So there's a positive distance between P and L. So you can find a point and a line with some non-zero distance. And there's lots of these pairs of points and lines, but since there's a finite configuration, you can find a point-line configuration where the distance is minimized. So you find a point and line whose distance is minimized, and there's a line down there. Now, every line, there's no ordinary line, so any line that goes through 2 points has to go through 3 points. So you have a point and now and a line with 3 points on it. And if you have 3 points on a line, 2 of them have to lie on one side of P. Or maybe one R might lie exactly in the middle, but on one side, 2 points have to lie on one side. And then it's just easy geometry that 2 points lie on one side of this perpendicular, then the distance between this point and this line is shorter than the original distance, and that contradicts the minimality of the original distance, and that is the contradiction. So that's a beautiful proof. Unfortunately, it's not a very robust proof. You try to use it to prove anything other than Sylvester-Gallai theorem, it's very, very hard to use it for anything else. But it is very pretty, so I showed it here. Okay. Now I'll tell you this Hess example that I mentioned earlier. If you, so you can see that we did use something about the real line, that it's ordered. Okay, the fact that you can divide the real line into two pieces like this, that's the ordered property of the real line. If you go to the complex plane, then it doesn't work anymore. And there's a counterexample coming from elliptic curves. So what's an elliptic curve? It's, you pick two numbers, A and B, complex numbers in this case, which have a non-zero discriminant, and you form this curve, y squared equals x cubed plus ax plus b, and that gives you a curve, which in the real line looks, can look like one of these shapes here. I'm not going to draw it in the complex plane because it's it's in 4 dimensions. As is well known, this is a group. You can put an abelian addition law on this curve. 3 points sum to 0 if they're collinear, and there's some degenerate cases when they're tangent, which I drew on there. So an elliptic curve is a group, and collinearity is just encoded as the relation summing to 0 in this group. And it turns out that in the complex plane, all elliptic curves have the group structure of the 2 torus, r squared over z squared. The classical Weierstrass functions tell you this. So elliptic curves in the complex plane, it's very hard to visualize, but they're actually a 2 torus in some sense. And 2 tori contain as a subgroup a 9-element subgroup. If you take the elements of order 3, or 3 torsion to be more precise, that's Z3 cross Z3, that's a 9-element group. And that's got lots of triples that sum to 0. So if you plot those 9 points, you will find that any 2 of them, the line between them contains a 3rd point in that configuration. So that'll give you 9 points. They're not collinear, not all collinear, but there are no ordinary lines. All lines are 3-rich. Okay, so this is a counterexample to the Sylvester-Gallai theorem in the complex plane. Okay, but this really shows you that something is going on. That you know, even though you start with just lines and points, more complicated objects, elliptic curves in this case, begin to appear. Okay, so the question that we were looking at, Ben and I, was something which is called the Dirac-Motzkin conjecture, although strictly speaking, Dirac and Motzkin didn't quite conjecture this. Okay, so you take n points in the projective plane, not all collinear. Sylvester-Gallai tells us that we have at least one ordinary line, so n2 is positive. But the question is, how small can it be? What is the least value of n2? We know it's at least 1, but how small can it be? So you can start building some examples. First basic example is that of Dirac-Motzkin, who showed that, who observed that if you take n is even, and you take the unit circle, and you take half the points on the unit circle equally spaced, and you take half the points at infinity on the line at infinity, which you have because you're projective plane, also equally spaced, or equally spaced directions, you can set it up so that the number of ordinary lines is just n over 2. And when you're odd, you can't quite do that, but you can modify Dirac-Motzkin's example either by adding a point, say the origin, or deleting a point. And you no longer get n over 2, but you get close. You get 3 n over 4, basically. Those are basically the best known examples, except for a few very small cases. When n is 3, you can do, n is 7, you can do a little bit better. You can do 3 ordinary lines. And n is 13, you can do 6, which is a little bit better than this 3 n over 4. So here's the Dirac-Motzkin example. Here's the unit circle with 6 points. So this is projectively transformed because I can't draw the line infinity undistorted. So this has been projected. I didn't actually draw this, Ben Green drew this, but it's been distorted. The line infinity has been moved to this black line over here. So the 6 points on the unit circle are equally spaced, although it's distorted, so they don't look equally spaced, but they are. And 6 points at infinity. the red lines are the ordinary lines, but all the other lines are not ordinary. They're all, okay, so there are 12 points and 6 ordinary lines. Yeah. And then you can add the origin, and that modifies the number of ordinary lines slightly. It creates a few more ordinary lines, but not too many. Okay. And then these are the 2 small examples. You saw the first one already, 7 points with only 3 ordinary lines, and here's a more complicated thing with 13 points, some at infinity, and 6 ordinary lines. Okay. So the Dirac-Motzkin conjecture is the assertion that this n over 2 is the best possible once you are bigger than 13 points. If you have 13 points, then this last counterexample of Cohen-McKee of 13 points with 6 ordinary lines, you can beat n over 2 in these 2 cases, but these are supposed to be the only counterexamples. Once you're more than 13 points, we believe that that n over 2 is best possible. You can't do any, you must have at least n over 2 ordinary lines. So this was never actually conjectured explicitly by Dirac or Motzkin, although Dirac said this was likely, whatever that means. But when n is odd, you can't even get n over 2. At least we don't believe so. So let's call the strong Dirac-Motzkin conjecture the statement that also, if you are an odd number of points, then you can then not only can you must have n over 2 ordinary lines, you must have 3 n over 4 at least. So what this is saying is that the examples I showed you earlier are the best possible ones. So so there's a lot of partial results on these problems. As I said, Sylvester-Gallai theorem already tells you that there's 1 ordinary line. There's a nice proof of Melchior, which we'll review in a bit, which up to 3 ordinary lines at least. Motzkin was the first to get a bound that goes to infinity, at least root n. And then Cayley-Moser got 3 n over 7, and then Siemens-Sawyer raises to 6 n over 13, but as long as n is bigger than 7, to get rid of the 7-point counterexample. So that was the state of the art for a while. And then what we did was that we showed that this conjecture is true asymptotically. So we showed that if you have sufficiently many points, if n is sufficiently large, then you must have at least n over 2 ordinary lines, and if n is even, and 3 n over 4 when n is odd. So the examples that I saw before are the best possible for n large enough. What is large enough? Our bound, we didn't compute it because it's terrible. It's like 10 to the 10 to 100. But that's an artifact of our proof. Surely we can do better. Okay. So that is the ordinary lines problem. Sorry, yeah, the Dirac-Motzkin conjecture. There's a related problem called the orchard planning problem. So rather than talk about n2, instead of getting n2 as small as possible, which is the Dirac-Motzkin problem, you talk about getting n3 as large as possible. So what's the most number of lines that you can put that are 3-rich? So you have n points, you try to make as many 3-rich lines as you can. So you can, if you interpret this poem properly or liberally, you can interpret Jackson asking this question in 1821. But it was asked a bit more formally by Sylvester 40 years later. So we want to make n3 as large as possible. Now, there's a trivial upper bound to n3 because every 2 points determine a k-rich line for some k. So you have a double counting identity, very easy to check. This is the n k's must sum to n choose 2 with the right weights. And this gives you, you work it out, a trivial upper bound on n3. It can't be bigger than 1/6 n squared minus 1/6 n. Now, you can do a little bit better than that because we have lower bounds on n2. All right, so n2 and n3 both appear in this sum. So if you have a lower bound on n2, that gives you an upper bound on n3. So, for example, if you know the Dirac-Motzkin conjecture is true, that there's at least n2 ordinary lines, you can improve this 1/6 n to 1/3 n. So you can get the upper bound n3 to 1/6 n squared minus 1/3 n. Okay, but that's not best possible. The reason being that the examples I showed you with this, with the circles and the lines and so forth, they contain ordinary lines and 3-rich lines, but they also contain this big line with lots of, there's also this other line which is really, really rich in this example here. There's a really rich line here, which also has to be counted in. So the the sharp bound on N2 doesn't imply the sharp bound on N3 because of this extra line, basically. So this is not supposed to be the best bound. The best construction, the best construction of a set with N3 as large as possible comes from elliptic curves again. So again, you take an elliptic curve, but this time over the reals rather than the complex numbers. Now, in the complex numbers, the elliptic curves look like a 2 torus. The group has the group structure of a 2 torus. Over the reals, it looks like a 1 torus, R mod Z, or sometimes R mod Z cross Z mod 2Z, depending on there's two types of elliptic curves in the reals. There's the connected ones and disconnected ones. So one looks like a circle, one looks like 2 circles. But in either case, you can find subgroups of this elliptic curve of order n for any n, and you can do a computation. If you take a subgroup of order n in an elliptic curve, you get lots and lots of collinear triples, because lots of elements in a subgroup order n sum to 0, and you do the computation, and you find that instead of 1/3 n, you get 1/2 n. You can check that the number of free rich lines is basically 1/6 n minus 1/2 n. Okay. And this is believed to be the best possible construction. Okay, so you can take subgroups. You can also shift certain cosets of subgroups also work. And there's one technical thing. There are some degenerate elliptic curves, which are not strictly speaking elliptic curves. They're just cubic curves because they have a singularity. There's 3 types. There's cuspidal, nodal, and acnodal cubic curves. The acnodal one also has a similar construction. Because it also actually looks like R mod Z. It looks like a circle, group theoretically. Okay, this is technicality. But so our second main theorem is again that asymptotically that's the right answer. That for large enough n, the elliptic curve constructions give you the maximal value of n3. Again, n naught is the Googleplex. We don't have a good bound for that. Okay. So these questions, I mean, it was nice that we could answer these sort of quite old, century-old questions. Although it wasn't really our main focus. That was sort of our bonus. I mean, we have all these classical combinatorial questions about how to exactly minimize certain quantities. But actually, nowadays, people also study how to not just classifying exact minimizers of objects, but approximate minimizers of objects. And that's also a very interesting question. And that actually really was the kind of thing we were looking at, we were more interested in. So the thing about minimizers to the Dirac-Motzkin conjecture or maximizers to the orchard problem are that both of those configurations have very few ordinary lines. N2 will be small if you're minimizing N2 or you're maximizing N3. In either case, N2 will be small, about big O of N. And all the examples we knew of sets with such few ordinary lines were very algebraic. They were always elliptic curves, circles, very algebraically structured. So you may remember in Tim Gowler's talk maybe 2 days ago, he observed the interesting phenomenon that for many combinatorial problems, the random construction is not the minimizer. It's often some algebraic object which is minimizing, and it's a very interesting question to me at least. Why is that the case, and why does minimizing a combinatorial problem seem to often generate algebraic structure which is not present initially in the problem? Where does algebra come from? How does algebra come from combinatorics? So this was what was interesting us. Why are the minimizers so algebraic? Or either minimizers or some near minimizers, sets with very few ordinary lines. And so what we found is that we found an explanation for this, that if you have a set of n points with few ordinary lines, like big O of n ordinary lines, then it must necessarily be structured. There's an inverse theorem, structure theorem, that says that such sets are always coming from cubic curves of degree 3. So a curve of degree 3 could be an elliptic curve. It could also be a union of a conic and a line, so like, for example, the circle and line infinity, or actually, or 3 parallel lines or something like that, or just one line. So all these examples, they all had a cubic curve involved, and we now know why cubic curves come in. Okay, so that's really sort of, actually our structure theorem is somehow, we consider our main theorem, and the other two theorems are corollaries. So our main theorems really are about sets with few ordinary lines. And so we have a bunch of structure theorems that describe what these sets look like. I think we have actually 3 or 4 theorems stated in our paper, but I'll just state 3 of them here. So there's an easy theorem, and then there's a medium theorem and a hard theorem. The easy theorem is easiest to state, is this one here, that if you have a set of endpoints with only kn ordinary lines for some k, so big O of n ordinary lines, then there's already some structure that you can, this set you can show is covered by a bounded number of cubic curves. Okay, the bound is not so great, 500k, but okay, but there's some bound. You know, if you take endpoints in general, it's very hard to cover them by cubic curves, because in general, a cubic curve will only pass through about 10 points at a time. So they're sort of collinear in the sort of cubic sense. Any configuration of few ordinary lines must be covered by a bounded number of cubic curves. That's our first structure theorem. This by itself is not strong enough to prove much of anything. So we have a better theorem. So again, if you have a set of endpoints with few ordinary lines, big O of n ordinary lines, but now unfortunately we have to assume that n is really big, double exponential, which is annoying, but that's what we're stuck with. If you have a lot of points and few ordinary lines, then rather than being covered by a bounded number of curves, of cubic curves, you can actually take a single cubic curve and cover almost all the points. That there's just a small number of exceptions, but almost all the points are covered by one cubic curve. This is a much more useful theorem, because you don't have to, because we understand how points are collinear on a single cubic curve. On many different cubic curves, collinearity is a complicated thing. But we actually have a better theorem than that. So the theorem which is really useful, and we use the previous theorems to prove this, is the following. So again, take n points with few ordinary lines, assume that you have many, many points, double exponential at least. Then after applying a projective transformation, which you're allowed to do, and after maybe adding or deleting a few points, we have a complete classification. Any set with few ordinary lines is basically one of the examples that I just showed you. That it's basically coming, they're coming from collinear points, or the Brodsky examples, points on the unit circle and points at infinity equally spaced, or a subgroup of elliptic curve. These are all the examples I showed you. You take those examples, you projectively transform them maybe, add or subtract a few points. Those are the only sets with few ordinary lines. Okay, so we have essentially a complete classification up to, well, at least for small k, okay, describing what these points look like up to constants. Now, once you have this theorem, the 2 main theorems I said at the beginning are corollaries, that you can just, to prove the Dirac-Motzkin conjecture and the orchard problem for large enough n, we have classified all the sets with few ordinary lines. You just check one by one how many ordinary lines and n3 each example has, and it's not so difficult to check that these conjectures are true. It also shows you that the extremizers that I showed you are the complete list of extremizers. Okay, so really it's the structure theorem that's important. Now, so where do these cubic curves come from? Why is it always cubic curves? So what we realized, well, this should have been obvious when we first started, but it took a while to realize this, is that what do cubic curves and lines have in common? Well, what is the connection between the two? And the connection is actually very, very classical. It's a theorem which is usually called the Cayley-Bacharach theorem, although the version that we use was proven a few years earlier by Chassos. So this is a very classical theorem in algebraic geometry. And it states the following, that if you have 2 sets of 3 lines, and they meet in 9 different points, then these 9 points are special, in the sense that any cubic curve that passes through 8 of these points passes through the 9th point as well. So here's the picture. There's 3 blue lines and 3 red lines meeting in 9 points, and then here comes a cubic curve. If the cubic curve hits 8 of those points, then automatically it has no choice. It must also hit the 9th point. Okay? So this is a fun, actually, it's not hard to prove nowadays with polynomials and linear algebra and so forth. It's a very cute thing. Bezout's theorem, I think, basically kills it off. But it's a classical theorem. It contains many special cases because there's lots of cubic curves. 3 lines, 3 different lines are a cubic curve, for example. And so the Cayley-Bacharach theorem includes Pappus's theorem as a special case. If you specialize to 3 parallel lines, a conic and a line is also a cubic curve, and if you specialize to that case, you get a classical theorem, Pascal's theorem. And an elliptic curve is a cubic curve, and if you specialize to elliptic curves, you get to prove that the addition law is associative for the elliptic curves. So it's a fundamental theorem. And this is, okay, so once you see this, then it's more plausible that cubic curves are relevant. But how do you actually use this theorem to prove our result? So we need another tool. So we need to go back to one of the proofs of Sylvester-Gallai. And not Kelly's proof. As I said, you can't modify that proof very easily. But there's another proof by Melchior, which is very nice. And this is the one that we used. So, okay, so Sylvester-Gallai, we have n points. We want to find an ordinary line. So the way Melchior proves is that he first dualizes. Instead of having n points in the projective plane, you have n lines in the projective plane, and you want to count ordinary points. Now, points that are only incident to two lines. Now, you've got these n lines now in the projective plane, so that they partition the projective plane into all these polygons. They form a partitioning of the projective plane into vertices, edges, and faces. And so now we get to use Euler's formula, v minus e plus f equals 1. 1 because the projective plane is Euler characteristic 1. And here, by the way, is where we're using something about R2. R2 has Euler's formula. C2 does not have Euler's formula. And neither does finite fields. Okay, we're using something about the real line here. Okay, so you dualize, so you got these points, lines, and planes in this configuration. You got vertices, edges, and faces. And there's various double counting, very easy double counting you can do to connect the number of vertices, the number of k-rich now points. So every k-rich point gives you a vertex, so you get the first sum. It also gives you k-edges, 2 k-edges actually, counted twice, and it gives us the second thing. And then you got all these faces, and faces have at least 3 sides, and every face, so if you call m sub s the number of faces with s sides, then f is the sum of the m sub s's, and every m sub s-sided face connects with s edges and so forth. So you get all these simple equations describing you what the vertices, edges, and faces are. So you plug this into Euler's formula, and just high school algebra, and then she tells you, oops, gives you a formula for the number of ordinary lines. That the ordinary lines, if you just plug this into Euler's formula, will soon tell you that the number of ordinary lines is 3, plus a contribution coming from k-rich lines for k at least 4, and plus another contribution from faces of size at least 4, of at least 4 sides. So this is just a simple computation, and this already gives you Melchior's bound that n2 is at least 3, because the other 2 terms are positive, non-negative. Okay, so that's Melchior's proof of Sylvester-Gallai. It's very nice, but this is a robust proof. I mean, a robust argument, because what this identity tells you, it tells you n2 is at least 3, but you can invert it. You know, if n2 is small, if there's few ordinary lines, it tells you that these other 2 sums are small. So if there's not many ordinary lines, Melchior tells you that there's not many k-rich points for k bigger than 4, and there's not many faces with more than 4 edges, more than 4 sides. Okay, so if you have few ordinary lines, Melchior tells you that you don't have many 4-rich or higher lines, and every face, most faces are triangular. Okay? So in other words, most vertices have degree 6, and most faces are triangular. So in other words, if you have few ordinary lines and you look at the dual configuration looks like a hexagonal grid combinatorially. The hexagonal grid is the combinatorial structure where all the points of degree 6 and all the faces are triangles. Now, you're not entirely a hexagonal grid. You know, if n2 is not exactly 3, you know, you can have a few places where you have maybe degree 6 or degree 7 or something, or maybe 1 quadrilateral somewhere. But at least locally, most of the time, you look like a triangular grid. Okay, so most of the time, so your dual configuration looks something like this: a hexagonal grid where all the vertices are degree 6, or most vertices are degree 6, and most faces are triangles. And now comes the really pretty observation, which actually is surprised. I mean, it hasn't appeared so not so well known. But if you take a hexagonal grid, if you have a configuration of lines and points which are arranged in a hexagonal grid, and you dualize it, you turn all the lines back to points and points into lines, the hexagonal grid configuration is exactly dual to the Cayley-Bacharach configuration. So here I've got 3 red lines and 3 blue lines and 3 green lines. And that dualizes to 3 red points, 3 green points, and 3 blue points. And all these vertices here, where the blue and red and green lines meet, dualize to lines. And what you get is that you get 3 lines and another 3 lines meeting in 9 points. It's exactly the Cayley-Bacharach configuration. So, so if you have few ordering lines, Melchior tells you that the dual configuration has got lots of hexagonal grid structure, which means that the original configuration, when you undualize, has lots of Cayley-Bacharach structure. And so what this means is that there's lots and lots of 9 tuples of points in your original configuration with the property that any cubic curve that goes through 8 of them goes through the 9th. And once you see that, now you can start seeing where you can start proving theorems. So you can pick 8 points, start getting a cubic curve. You draw a cubic curve between those 8 points, you can always do that. And then this curve will automatically hit a 9th point, and because the grid just goes on and on and on, you'll hit more and more points. And you can do a counting argument, and you can find lots of counting cubic curves that pass through lots and lots of points in your configuration. And this is basically how we prove our first structure theorem, that if you have only k in ordinary lines, then this argument will eventually tell you that you can find cubic curves that between them, they each have lots and lots of points in P, and you can cover P by about 500k cubic curves. Okay, so that's how we got started. You can do better than this. So you've got all these cubic curves, but if lots of points lie on one cubic curve and lots of other points lie on other cubic curves, it turns out that these sort of points, they don't interact with each other very much. They can't generate many sort of good cubic curves in common. You can't create one of these grid structures with like half the points on one cubic curve and half the points on another cubic curve if those curves are like irreducible conics or irreducible cubics. Basically because Bezout's theorem will stop this from happening. So you can show that of these 500 cubic curves, at most one is nonlinear. You can have one conic or one cubic, but everybody else has to be a straight line. It's for a rather tedious combinatorial thing. But basically, you can show that you can cover your set by one cubic curve and then a whole bunch of lines. And then the difficult thing is to deal with all the lines. So the model problem is that suppose that your set of points is covered by a small number of lines. And what can you say about those lines? And it turns out to be some model cases. One model case is that suppose your set P is covered by 3 non-concurrent lines. So there's 3 lines, not all concurrent, and your points all line on 3 lines. Wow, what is the situation there? How can you create a few ordinary lines there? Then you can generalize that to the more general non-concurrent case. Now you have k lines, not all concurrent, no 3 which are concurrent. What can you say about that case? Then the opposite case is the concurrent case, or by projective transformation, the parallel case. Suppose your set just lies on k parallel lines. What can you say about ordinary points, ordinary lines in that case? So these are 3 cases that you have to understand. To do the triangular case, it's kind of cute. Every single case we had to deal with, we had to discover some classical theorem from the 19th century or something. Well, in this case, from ancient Greece. To deal with the triangular case, if you have all your points on 3 lines, the tool that ends up being used is Menelaus's theorem, that 3 points on 3 different lines are collinear if and only if certain ratios add up and multiply to 1 or minus 1, depending on your conventions. Okay, so that's a very classical theorem from Greek geometry. And so it reduces the question to actually one of additive combinatorics, which was very fortunate for us because we actually knew that subject, about understanding how what kinds of numbers multiply to 1. And so the question using Menelaus's theorem reduces to a combinatorial question, which is the following. Suppose you have a finite number of non-zero numbers. So in some talks, in Ben's talk and some other talks in this conference, we talk about sum-free sets and product-free sets and so forth. This is the opposite. This is sort of sum-full or product-full sets. These are sets that almost every product in your set lands back in your set. So suppose you have a set such that, well, actually the theorem is that can't happen. That if you have a set of n real numbers, then most pairs must actually escape your set. You can't find a set of n points which are basically almost closed-end multiplication. And the reason is that the real line doesn't contain finite subgroups. Well, it contains one. I mean, the 1 minus 1. It contains one non-trivial subgroup, but it doesn't contain any large finite subgroups. So it turns out that you can't get anything close to it, to a subgroup either. So you have n points in the real line. You can easily show that many of them escape. Okay. And this tells you that 3 lines cannot generate a set of few ordinary lines. If you want to do the more general non-concurrent case where you have many lines, more than 3, then you have to use Menelaus' theorem over and over again and iterate. And if you do it, you'll soon see these fractional linear transformations come up, because you're always converting ratios to other ratios, and this is what fractional linear transformations do. And so you can't just use products; you have to also introduce fractional linear transformations. But fortunately, there's a nice tool of allocation, Incidence, and Rouge that we can just use pretty much as a black box. It's basically a sum product type result. That if you have n real numbers and a fractional linear transformation, then either the product set A times A is large, or if you fractionally transform A, FA times FA is large, as long as F is not self-linear. So one of these things is large, and that you can use to show that if you have K lines not all concurrent, then you don't generate too many ordinary lines. You must generate lots of ordinary lines. Okay, so then the last case is the parallel case, and Ben and I had this really ugly, difficult argument that gave terrible bounds for this. And then this undergraduate at Cambridge, I don't know if he's still an undergraduate, Luke Betts, gave a very slick proof of this. It was very nice, and so we added it to our paper. That if you have endpoints which are on say k parallel lines, or dually, if you have n lines that point in only k different directions, then you must generate lots and lots of ordinary points. So if you have n lines and they only point in a few directions, that's like 3 different directions, then there must be lots and lots of points that are only incident to 2 lines. So his proof is really cute. It again uses the properties of the real line. In this case, it uses convexity. So here's a configuration of a whole bunch of lines that only point in 3 directions. And you want to show that there's many, many ordinary points that only incident to 2 of these lines. So what you do is that you take all the ordinary points, all the non-ordinary points that are incident to 3 or more lines. So there's some finite number of non-ordinary points. You take the convex hull, and you take an extreme point. You take a non-ordinary point that is extreme, such as this point V here. So this point is incident to at least 3 different lines. So you take the 2 lines that are sort of closest to your convex body, and you can then just some convex geometry shows that every point that these lines meet is going to be an ordinary point because they're not in this convex hull. So you can just use a very simple convexity argument, as it turns out, to start finding lots and lots of ordinary points. This is not the full argument, but this is the main idea. Use convexity and just an iteration argument. So this handles these model cases of parallel lines, non-concurrent lines. Then there's the general case where some lines are concurrent, some lines are non-concurrent. That's a bit messy, and we have to use a pigeonholing argument to somehow reduce that hybrid case to the model cases. And it's in this pigeonholing argument that we lose a double exponential, and that's very annoying. And if we could do this case better, then we wouldn't have this double exponential. But if you do this iteration argument, you do get this second structure theorem. Okay, that you can find that almost all points lie on a single curve. All right, maybe I'll skip. Okay, well, and once you're on a cubic curve, then you've got a group law, and then you can do some additive combinatorics to show that the points on your curve actually look like a group. Maybe I'll skip that slide. And then finally, there's a few points that are still outside your cubic curve, and you have to show that there are not too many points outside your cubic curve. And what happens is that what you find is that if you have a lot of points on the cubic curve, and you add or subtract some new points to your configuration, every point you add or subtract to a configuration tends to increase the number of ordinary lines quite a bit. It's very hard to modify one of these special configurations, like an elliptic curve subgroup, in such a way to decrease ordinary lines. You usually increase. And to prove this, we found this very nice result of Poonen and Rubinstein. It's actually, it's a very cute statement. That you take a unit circle, and you take all the roots of unity on the unit circle. So that's this dense subset of the unit circle. And you take all the chords between roots of unity. That's a lot of chords. That's an uncountably infinite number of chords. But it turns out, well, and a lot of them go through the origin. So the origin lies on an infinite number of these chords. But that's the only point it does. Any other point that is not the origin and inside the unit circle, it turns out it only lies on at most 7 chords connecting roots of unity. It's a very pretty result. There's a controlled multiplicity of this infinite set of chords. So they proved this theorem. I forget why they needed this theorem for some application. It's a very nice application of Galois theory, and it's computer-assisted too. It's a computer-assisted proof. But what this tells you is that if you already have if you have an example of lots of roots of unity on the circle, and you add a point in the middle of the circle, not the origin, then you would create more ordinary lines than you delete whenever you do that. And so you can soon show that it's not efficient to sort of perturb things like the unit circle. We also need variants of this outside the unit circle and also for elliptic curves, so we had to prove those separately. But this result comes in. And that's what gives you the full structure theorem, that the sets of few ordinary lines, they're either collinear or they come from equally spaced points in the unit circle, or they come from a subgroup of the elliptic curve up to a projective transformation and up to adding or removing a few points. Okay, so I guess it's appropriate to end with some open questions, since that's what Erdish was so good at. We have the structure theorem for sets in R2 or PR2 with few ordinary lines. You can ask, so Sylvester-Gallai is not true of the complexes, but maybe the structure theorem is still true. If you have a set of lines in the complex plane with few ordinary lines, is it still true that they come from cubic curves? Is it some structure theorem like the one we have? And the only examples we know suggest the answer is yes, but our proof method, our first step breaks down, or almost first step, because we use Euler's formula very early on, and I don't know what the complex analog Euler's formula is, because we have all this homology and Euler characteristic and so forth, but that doesn't seem to be directly useful. If you replace lines by other sets, so many of the earlier results about ordinary lines and so forth, you can replace lines by algebraic curves or pseudo lines, and that still works. But we use the Cayley-Bacharach theorem, which is a very pretty theorem, but it only works for lines. You replace it with some others, you replace lines by something else, our proof breaks down. We understand sets with very few ordinary lines, big O of n. Actually, our arguments tell us also big O of n log n, basically, we understand. But this is double exponential, which stops us from getting much better than that. So there's this, most of the points have actually n squared ordinary lines, but what about sets with, say, n to the 3/2 ordinary lines? We don't really have good description of those. We should get better constants so that, for example, so that you can actually finish the proof of these Dirac-Motzkin and Orchard conjectures, not just the asymptotic case. And of course, finally, we should end with Erdős' question, which is still unsolved. If you have n points and no 5 on a line, can you show that you don't have that many 4 points on a line either? Okay, thank you very much.
Any questions? Comments?
I don't. I have to think. It reduces. The way they prove it is that they reduce to showing that a certain. If you have a point which lies on many different, in fact 3. If a point lies on 3 chords, you can show that this implies that there are 12 roots of unity that sum to 0, and they have a classification of all the 12 roots of unity that sum to 0, and there's a lot of Galois theoretic conditions on what these roots of unity have to be. and they use a computer I think they even need the computer to show that it's a finite family, that the modulus is finite or irreducible configurations. That's a good question. I think there's no non-computer system proof. Yeah.
Any further question? Yes, one more over there.
No, actually. Well, the only example I know how to analyze are basic cubic curves, like elliptic curves. And so for a cubic curve, you can make n3 big and n4 0. And you can also do that over the reals. But there's nothing higher. There's no other groups, no other complex variety curve. There's no other abelian varieties in the complex plane other than the cubic curves. Which is sort of why you believe this conjecture to be true, because there's no more algebraic obstructions. And besides, if Erdős proved it, it's probably correct, right? So.
Any further questions? If not, then let's thank. Next talk is in 40 minutes.